Hi everyone, my name is Cárdenas. I am from the Santo Tomás University in Colombia. I'm going to present a paper with the title Optimal PID Access Control for IAV Quadrotor based on Multi-objective PSO. This is a project in collaboration with the Bethune-Cookman University in the United States. So first, we are going to present the system overview and what are the design criteria for the controller and which are the problems with control with drones, then which control methods are available and why we choose the Parrot optimization with algorithm for tuning this control, and then we compare some cost functions and intuition and feature group. So let's say we have a IAV Quadrotor. This has 4 rotors and well, it's a aircraft with now in reception because it has many capabilities such as vertical takeoff landing and operational flying and many others. And in this figure, we can show that it has 2 systems of reference. One is the movement in the war, and the other one is the rotation in the body frame. So we have 6 degrees of freedom. And for control this axis, we have to, for main applications, we need to first ensure the stability of the system. Then we can think about that the system responds in a short time and in a small error. We need to ensure its robustness, like there are many disturbances, many uncertain things in the model, and we have to think about the efficient energy consumption. But this is not easy because the aircraft is a stable system that is under-actuated because we have only 4 rotors, 4 actuators, and it's 6 degrees of freedom. And we cannot control everyone directly because the actuators are over the theta axis. So we need to do it indirectly. And it's a nonlinear system. It's coupled because some variable states depend on each other, and it's obviously multivariable, and there are many environmental uncertainty. For example, in this model, think about this model. Here we can watch the equations based on physical laws, forces, sumatories, and based on that we define a state vector that is mostly the position on the war and the rotation of the body and his different derivative states, velocities. And we create our state space, so you can say it's not linear, there are cosines and multiplies. And I think personally it's awful, it's so complex. And here we are considering some forces and torques that are defined here that are proportional to the quadrotor speed. But this is just a classical assumption. We have to say that this is a perfect symmetrical structure, that the inertia matrix is symmetrical, and we have many assumptions, many problems that when someone wants to implement this in a real world application, we have some other problems, like for example, this is a dynamic model that depends on air pressure and temperature that constantly is fluctuating. We have some disturbances like wind speed, like if we interact with other vehicles, we have also some problems. And for some specific applications, we have match changes, for example, in delivery patterns. And also in this model, we are not considering aerodynamic effects like drag, like ground effects, and so on. And also there are uncertainties that some parameters are difficult to calculate, for example, the coefficient of inertia. So to handle with that, there are many control approaches based on adaptive control, geometric control, robust control, and recently there are so many investigations in the field of reinforcement learning and intelligent control with artificial neural networks. But we propose the same classical methodology with PID controllers. This is the classical system in which we have some controllers for each axis, and for the axis x, y, and rho phi. We need to have a two-loop controller because, as I said, we cannot control it directly. And then we have a control mixer that converts the output of the controller to the signal of the rotors. And the PID controller is a classical controller who is really useful in the industry because it's easy to implement and also has some robustness, I would say. The problem here is that we need to estimate these constant, these parameters that are going to give some kind of weight or importance between the present error, the past error, and the future error based on a derivative and integral error. But for that, we propose plan the system like an optimization problem in which we want to find these parameters that reduce some kind of error. So we propose use the particle swarm optimization algorithm, which is a bias-fired algorithm based on the behavior of swarm animals, swarm colonies, like ants, for example. It's been proven that it's very useful for nonlinear optimization, and it's effective and easy to implement, and it's flexible for many modifications. So the idea of this algorithm is share some knowledge based on where the best particles or the best location are located, and explore towards this direction. There are some works related to it. There are some old works based on the idea to tuning algorithms is a problem that has been handled since a while, and mostly are with genetic algorithms. Also, with this problem of the model, there are proposed model-free controllers, for example, the fuzzy or deep neural network models that are more recently worked. Then we have the applied PSO algorithms that are proposed mostly for not complex optimization and non-linear optimization, but also recently in robotics application in search and rescue operation. But in this time, we are going to use these algorithms to tune PID that are some works here where they compare and they evaluate some functions for this. So what we propose is to use the algorithm that is as follows. First, we initialize the system in the particles around the space, and we, in each iteration, we calculate the next particle position based on the current velocity. It's only the current position plus delta factor plus the current velocity. And then we update the velocity based on this equation, which means that we are going to share the position of the best particle. We have some parameters that we have to tune. This W is the weight inertia, which means that I'm going to continue following the same path that I had. And then we have the personal coefficient, which means that I'm going to follow my own coast, on the work, and then we have global or social coefficient that is I'm going to follow the path of the other particles. So the idea here is follow where are located the best particles and help to explore in this section and don't lose time exploring where there is anything. Then there are some improvements to this method. We add some repulsion in the particles so that the particles doesn't go in the same. They keep a distance to explore more area. And next we have some exploration strategy that is or at the beginning of the episode, we have to explore more the environment, and then we chose where to search more. And then we update this exploration probability that we suggest to do it with this equation. And something important is don't lose time in a stable system, in stable particles, because they take a while to convert, so it needs more time. So what we do is initialize a new particle in just a random position, and then we iterate until it converges. We update the best particle position based on Parrot. That means that we have some cost function that we explore, and this is the idea of this paper, see which kind of functions we have based on control parameters. We implement this system in MATLAB with two experiments. One is a step system, and the other is a set point. And we have these parameters. These are the parameters of the PSO, and these are the results. So as we have here is that in the first experiment with the step response, the functions that normally are used for this kind of experiment that are median square error and median absolute square. Well, it helps with the system, but we propose for this two new cost functions that are better than the system. And if we compare the first experiment with the second experiment, we can notice that the second experiment it has a better response. We can compare it here with the initial controller, which we can have that the control base has many oscillations, and it takes a while to convert, to stabilize, and it has more, an overshoot. If we compare the control signal, we can notice that the two controllers that we choose based on our cost functions were with a loss control effect. So in terms of numbers, the system, the PID that we tuned was optimized around 0.5% of the overshoot, and it's stabilized around 4 times faster. So to conclude, our algorithm could find 7 better rates PID constant with 8 attempts, and well, based on our functions, overshoot, setting time, and integral square. And we suggest tuning directly the system with this capacitor because it helps to obtain a better response. The loss function that we proposed were found useful and better compared to the normally used median square error and median absolute square error. And this method is easy to extend it to other systems because we don't need like a model to tune our system. For future work, there is a lot to do. First, we need to think about how tuning all the axes because we only tune one. At the time, supposing that the system doesn't interact with the other axis, which is a supposition made, we have to make an approximation. And well, there is a lot of problems like how we can handle with different operating systems, operating points, or how to make this problem in a real environment. Okay, so thank you for this. So if you have any questions.
Yeah, thank you for the presentation. Are there any questions?
One small question. What is the advantage of your method compared to classical methods such as the Riccati control and so on?
So shall I pass?
In comparison to classical methods such as Riccati control or other state space controllers?
You mean for optimization problems? Or for control problems?
No, for controlling the aerial vehicle. So have you compared the control performance to other classical controllers?
Well, in terms of controllers, there is not like such a big difference. It's only, I mean, it's just a classical PID. It has the problem that a linear controller has. Like, for example, when he's out of the operating point, there are, well, the system is non-linear, so there are some limitations. The system is not going to respond as well. So in terms of the control, this application is just a simple PID. It was not the idea. The idea was more about how to tune, how to get these parameters in order that the system responds as well as we could. And in these terms, I think that the idea is that we don't need to have a model for that. So we can design a system for example, what happens if we have a center of mass that is not in the center, in the origin. So our colleague explained a method. We need to adapt inertia matrix. But in this case, we don't have to do it. If we want to model the system with drag or another aerodynamic problems, well, in mathematicals, in other approaches, will be really expensive, really expensive. But here we don't have to do it. We just need to run the algorithm.
And do you think that you can use the method of particle swarm optimization for the control parameters also with a state space control or something?
Yeah. The thing is that we have to think that in this case we tune only these three gains. But if we have, for example, in this case, we are visualize only two dimensions, P and I. So the more we variables we need to tune at the same time, the system or the space of search is going to grow exponentially. So if we want to tune state space with 12, so we have a 12-dimension space. So I don't think it's really effective. But for little, we can split the problem, for example, and make several problems. I don't know. This is one of the future work, tuning all the axes at the same time, for example.
Okay, thanks.
I have the question, how long will it take this PSO?
Yeah, the algorithm itself is not that expensive. I mean, this algorithm is easy to implement, it runs faster. The problem is with the data, with how we evaluate the system. In this case, we are using a simulator, so we need to try each particle what evaluation has. If we have a model, we can use the model, which could be faster, but it's not the idea because the idea here is not use the model. Or we can use it with real data. In this case, it not depends on the model, but how we are going to evaluate the system. For this case, it takes around each simulation, it takes around 5 seconds. And we run this with 50 particles and 100.
5,000.
Yeah. So
divided by 5.
yeah. So it's around. And we run for each. So we're eight times. Around 40,000 plus 5.
Maybe crazy idea. Do you think it's possible to use this approach for like online fine-tuning or adaptation of the
Yeah. This is an interesting approach because it is possible, but well, we need. There are some several approaches here. We need, for example, maybe with the drone would be a little difficult because we need to ensure stability. Because otherwise, if we have an online system that is unstable, we can damage the system. So we need to consider only that the system is unstable. For that, we propose limit the search space based on stability. We can use, I don't know, which tool is Japanese and others. And we need to consider this.
In my opinion, there is a problem related to this kind of tuning because, first of all, you are actually tuning the parameters by PSO by performing simulations. You are using PSO because you are not aware about the exact model of the system. What is exactly the system? Is it because it is affected by uncertainties on the parameters, and also you are not considering some non-linear behaviors within your model. But you are using a PID controller, which is not the best option in such kind of system, non-linear system, and with uncertainties on parameters, and also considering the effects of external disturbances. But actually, you're using an optimization method which is able to find the global optimum of among the parameters. So, from one side, you are trying to best optimize based on a model which is supposed to exact representation of the system by using a really powerful optimization method. But on the other side, when you will apply to the real system, which is not exactly the model, you could have a very different system behavior, because you're using a PID controller which is not really robust with respect to many all the previous aspects. So considering nonlinearities and disturbances and so on. The other point is that for each iteration, you have to evaluate for each particle the cost function, which means that if the simulation, the duration of the experiment is 5 seconds, you have to multiply for each particle this in the experiment. This, if you want to do it in the practice, this experiment multiplied for each particle and considering all the iterations, which makes quite difficult to optimize in reality with real experiments the controller. So, in my opinion, I don't know if you agree with this. probably using a more robust controller would be a better solution, even considering optimization just in simulation and not in a real experiment, which I think it's not really feasible.
Okay. Yeah, this is one of the biggest problems of this system. Let's say, well, there are some proposed solutions. Well, for the nonlinear model, in this time we are only tuning for one operating point, but we can run this algorithm for many operating points, and then I don't know, we can use game scheduling or FUSI for mix all the systems for a nonlinear model. So somehow this would work the simulation, but when we implement it in real life, we have this problem that we need a way to have the data and evaluate the system. At the moment, well, I don't have the answer for that. It's something that we need to review.
Maybe iterative approaches would be much more feasible because you don't have to start the drone and make the experiment for each iteration for each particle. I mean, some iterative learning approaches maybe would be better.
Yeah, what we suggested is, for example, it could be really useful for define some regions where the system would work. Just imagine you have a region with stability here, and the algorithm converts to this zone, this zone, this zone, or this zone. You define some regions where if we have, the system in real life should be work pretty well, so you don't have to do, you only have to do some modifications, not that much, but maybe it could be really useful for have like an idea of an approximation.
Okay, I must stop your discussion. It's interesting, but you can continue for the dinner and during the evening.